So as Xander mentioned, Alicia Espeleta was the lead person on this project and used it for her master's thesis. Kristen Shive was also very much involved and carried out all the field measurements for the sampling, which was part of her master's thesis at NAU. Carolyn Sieg with the Rocky Mountain Research Station has supported this project since right after the Rodeo-Chediski fire itself, which is the original starting point for this research. Andrew Sanchez-Metter at NAU worked with us on the modeling and has a lot of experience with FVS modeling and that whole modeling environment within the Forest Service. And then Barb Strom, also here, did her master's degree through NAU right after the Rodeo-Chediski fire. And in the big picture, what we're presenting tonight is using a climate-sensitive model to compare with the results that Barb carried out not that many years ago without using a climate-sensitive model. And we get a very big difference in the answers. So let me move forward, there we go. So this is a particularly interesting moment to be talking about climate change issues because this very week, the Intergovernmental Panel on Climate Change is meeting and releasing their 5th assessment report from the first working group. So the IPCC is the international body that's bringing together basically the global scientific community to look at climate change. They've done 4 assessment reports. The 5th one comes out this week, day after tomorrow, the first part of it. The first part is the physical science basis, and then after that they look at the implications in terms of economics and social implications and things like that. But it's an exciting moment to be talking about climate change. And it's a very relevant moment for us in the southwestern U.S. We have many millions of acres of relatively dry coniferous forest. We have a very small amount of quite wet forest like spruce and fir or aspen forest. We have many millions of acres of ponderosa pine and dry mixed conifer. And we have 2 trends that both go in the same direction to create severe fires. The first that most of us are very familiar with is fuel increases due to land use changes. And this is the long-standing situation of excluding fires, logging of big old trees, the consequent eruption of populations of small dense trees, creating fuel ladders, creating a lot of canopy fuel continuity and supporting fire that way. The second trend, which is becoming increasingly apparent in recent years, is the relationship of warming temperatures to drier fuels, longer fire seasons, and higher fire severity. And with both of these trends going in the same direction, that's a major problem for conservation of these forests. So fuel treatments, such as tree thinning and prescribed burning, reduce fire severity. And that is very clear. It's certainly clear in the Rodeo-Chediski fire and in many other studies and in meta-analyses comparing studies from many experimental and observational sites. So we see that fuel treatments do work. But an important question, and the one that Barb Strom addressed in the publication mentioned at the bottom of the graphic here in 2007, is what are the long-term differences? So she looked at sites that were burned on the Apache Sitgreaves National Forest in the Rodeo-Chediski fire, so shown in the lower right. That's one of the photograph and the statistics given there are part of what was going on with that fire, which ended up at close to 500,000 acres, was by about an order of magnitude the largest fire to that date in southwestern history. And just less than a decade later, we had surpassed that with the Wallow fire a couple of years ago. So we're really about at the limit now of how much contiguous forest we can put together to burn in one fire, but we are at that limit. Well, in the case of the modeling that Barb carried out, that modeling showed that fuel treatments made a difference, not only at the time of the fire, but they had a persistent effect that continued on and was still evident 100 years into the future. But the analysis that we worked on together did not incorporate climate change. So I want to turn and talk a little bit about some of the relevant points of climate change related to the fire situation in the Southwest, and then look at how we used the newer Climate-FVS model, Climate-FVS, in order to simulate the same situation with a model much more capable of responding to climate. Somehow I did something bad to the screen.
Well, we can still see it. I will advance the slide for you.
Okay, thank you. There we go.
Oh.
So slide 4.
There you go. Great.
Okay. All right. So on slide 4, this is some of these kinds of pictures are very familiar to a lot of the people in this audience, but as Andrew was mentioning in the introduction, there might be people looking at this from other places. So these are examples of thinning and burning treatments in the Southwest. The top example is actually from near Flagstaff. It's not the actual study site, but it was done by a professional photographer who did a nice job of capturing the exact same group of trees. So you can see the difference created by thinning here. And it's a similar type of process that occurred on the A-bar-S, which is short for Apache Sitgreaves National Forest. And similarly to what's shown in these pictures, the trees involved, they're all pretty young. Some of them are reasonably large in diameter, maybe 16, 18 inches or so, but they were quite young ponderosa pine trees. In the lower picture is an example of prescribed broadcast burning, which is what was done on several of the sites in our study. A couple of these sites were pile burned rather than broadcast burned. Okay, so to look at what we see now in terms of climate change and fire, basically we see warmer temperatures, reduced snowpack, earlier snowmelt, and more fires tracking temperatures. So in the left-hand panel here, you can see all those red dots. Every dot that's red represents a weather station, and the size of the dot is showing the degree of warming in the last half of the 20th century. And as you look across the western U.S., you can see that they're almost all red. There are very few blue dots. You can also see that the Southwest is actually not taking the worst of it. The West Coast and up into British Columbia look to be some of the places that have the greatest increases in temperature in that period. If you look at the panel in the upper right, the one that says A, this is from a study by Tony Westerling and others, a very widely used study that looked across the whole West and showed in that panel that wildfire frequency is tracking temperature changes in the western states. You can see the black line tracking those red column bars quite well, and you can also see that there's really a qualitative change going on in the temperatures after about 1985. After that period, almost all of the years are warmer than the years before that. The panel B right below it is showing timing of spring snowmelt. And so that's moving increasingly into the pink lower band, which is called early snowmelt. So as you have earlier snowmelt, that means that water is being lost in the form of snow, that fuels are drying out faster, and so fire seasons are getting longer, which makes ultimately forests more vulnerable. And that's what they're getting at in the middle panel. That's also from the Westerling et al. Paper, where they're trying to track relative vulnerability of forests to warming patterns. Now, everything that we see on this graph, none of these things are predictions or computer models or any such thing. These are all observations of, especially in the last about 2.5 decades, of increasing temperatures and the associated increase in fires. When we look at this next graphic from Seeger et al., this is showing predictions of the future. And what we have here is a really interesting graph. On the y-axis, we have a value scaled in millimeters per day, and this has the unfriendly name of P minus E anomaly, which means precipitation minus evaporation. So water coming in minus the water going out. And anomaly just means compared to an average. So the average is the 0 value on this graph. Let me see if I can, there we go. Does that show up, Xander, that arrow?
Not yet. You have to click on the graph. Did you click yet?
Ah.
There we go. Now I see it by the 0. Good.
All right, great. So the arrows is showing the zero line. The zero is the long-term average of the difference between water coming in, water going out, so it's a way of measuring dryness. They initialized the model in 1900 and ran it forward to the present. So for over 100 years, they had actual data to compare the model performance. And you can see that all these colored lines are moving forward in a fairly flat way. The line that's red is the median of 19 different climate models, and then the pink bands are the middle 50%. So we don't have any one perfect model to use for climate. We use multiple models, and we basically see if they're consistent. So for the 20th century, we have a pretty consistent report of no real change in moisture, except as you get towards the end of the 20th century, the last couple decades start to look a little bit drier. But now, with having some faith in the performance of these models, if we turn and project them forward for the next century, then we see the pattern that you see on this graph, which is basically moving downwards into the negative territory on the y-axis, which is to say drier conditions. The median's moving down. The pink band, which is that middle 50% of model outputs, starts to get wider, so there's less precision associated with these estimates, but there's still a lot of consistency. They're all moving in a downward direction. And if you glance at the title down at the bottom of this paper, their title was Model Projections of an Imminent Transition to a More Arid Climate in Southwestern North America. So that's, it's not good news, but it's what these models are showing us. This slide is showing very recent work by Park Williams, who looked at similar kinds of conditions and then thought about how trees respond to these climatic conditions. So he took tree ring records that have been collected in many, many places around the Southwest, which, as many of you know, is a real center of dendrochronology and networks of tree ring records from long-lived trees. And he looked at how climatic factors were expressed in terms of tree growth, which gives us a spatially explicit network of sites for several hundred years into the past, sometimes for millennia into the past. And he used the climatic and tree growth records to come up with this FDSI, or Forest Drought Stress Index. This is kind of like the PDSI, or Palmer Drought Severity Index, that we're familiar with. The idea of using an index like this is to take records that come from different places or different species and put them in a uniform fashion so that they can be, as a standard index, compared with each other. So if you look at panel C here, this is showing cold season precipitation, and similar to the Seeger et al. Example, we have the last 100 years and the next 100 years. You see little change in precipitation, but if you look up at panel B, you see the trend predicted for warm season temperature to move sharply upwards in the 21st century. And so if you look at panel A at the top, then if you have, as a simple calculation, about the same amount of water coming in, but more going out because of increased warmth, ability of air to hold more water, we get a stronger vapor pressure deficit, more drier conditions, more drought. So as Williams then in the bottom panel, the Forest Drought Stress Index, takes that and applies it to the projected growth of trees in the future based on that relationship between vapor pressure deficit and tree growth in the past that he reconstructed from the dendro records, what you see is a decline starting around now, or maybe even in the 1990s, and moving progressively downwards in the 21st century. The last interesting feature on this graphic is where the arrow is pointing now at this brown line that appears, it's just a horizontal line in the bottom panel there that appears below the zero line. That marks a threshold of the conditions that regionally across the Southwest in this reconstruction, the conditions that he found were the severest climate conditions that trees had encountered in that period of the tree ring record. And you see that around the year 2040, 2050, somewhere in there, the forest drought stress index is projected to cross that threshold. So this is the kind of forecast for climate change that we see at this point. I just want to pause for a second and just ask Sander, is the sound coming through okay? Or are we?
No, you're doing great, and
well?
the visuals are working, so full steam ahead.
All right. So in the intro, Xander mentioned about some practical questions, and so one really practical question that one might ask is, well, are we screwed? Does it make sense to carry out forest treatments? I mean, there's some other really big picture questions. Does it make sense to try to conserve endangered species? Does it make sense for us to rely on certain watersheds and so on? There's a lot of questions associated with climate change, but the specific issues of forest conservation, restoration, and management, we can ask whether treatments, a little bit like this landscape shown in the picture, whether they make sense. Oops. Okay, so the specifics of the study that we looked at here come from the Rodeo-Chediski fire, which burned in 2002, and it burned over a mosaic of treated and untreated sites. When you look at the graphic there on the left, a couple points about it. One is that this fire was so big that you could see the outline of the fire on a map of the whole state of Arizona, which is remarkable. It burned on lands of the White Mountain Apache tribe and also the Apache Sitgreaves National Forest. And our group has worked with both organizations, both landowners, but right now we're talking about the Apache Sitgreaves National Forest. And in that forest there were patches of areas that had been treated within the previous 10 years before 2002. In 2003, after the fire, staff from the National Forest and the Rocky Mountain Research Station selected 7 paired sites, paired in the sense that they had about a 10-acre treated area and about a 10-acre untreated area, close by, similar topography, similar vegetation type, same elevation, etc., in order to draw some comparisons. And with some support from the Rocky Mountain Research Station and the Ecological Restoration Institute at NAU, we were able to measure those sites in 2004, and then with follow-up funding from the Joint Fire Science Program again in 2011. And one of the questions we asked was, did these treatments make a difference in terms of the behavior of the Rodeo-Chediski fire in 2002? The answer to that is yes, and I'll show you a little data on that in a second. But the long-term question that we're trying to look at here is, how do these sites change over time? What are the longer-term legacies of these treatments? And most recently, how does climate affect those changes? So in order to do this, we use the Forest Vegetation Simulator. So this is the rather familiar Forest Vegetation Simulator modeling package, which is the most widely used forest model in the U.S. and is used by all sorts of government agencies, by researchers, and so on. FVS, as I think many of you know, is not one model per se. It's actually a set of regional models. So we are looking at the Central Rockies variant and the Southwest ponderosa pine model within that Central Rockies variant. But they're packaged together in a similar software, use similar sorts of data inputs, and in general, these regional models are highly accurate and quite precise because they're based on long-term studies of tree growth in different kinds of competitive environments with very strong data that has allowed them to be very reliable models. The fundamental problem, though, of relying on the statistical relationship of growth that's been measured over many decades is that if the conditions at the sites change, as the climate changes, then those statistical relationships may no longer hold in the same way. And so Nicholas Crookston and Gary, now I'm sorry I'm spacing out on his first name, and Rayfelt carried out analyses of climate-forest relationships in order to make adjustments to the FVS simulator that would allow it to incorporate effects of climate change. And we'll go through that in a little bit more detail here in a second. So our goal here was to use the Climate-FVS model in order to reassess the results of the Rodeo-Chediski fire, taking climate scenarios into account. Okay, Gerald Rehfeldt, I'm sorry about that. So this paper from 2006 shows empirical comparisons of plant-climate relationships for the western United States currently and projected into the future. So the panel that's displayed here is for ponderosa pine. You can see very large distribution across pretty much the whole West. If you look at the current panel on the left, you see ponderosa, a lot of ponderosa in the Southwest, for instance. If you scroll across then to the panel on the right, 2090, and look at the Southwest and look back at the current situation, you see that those black dots are starting to get a lot thinner on the ground. Meanwhile, if you look to the north in Colorado, you can see that as Arizona and New Mexico, as their area of ponderosa pine growth is projected to decline, Colorado, for instance, and Utah are projected to increase in suitable habitat for ponderosa pine. And this kind of analysis is focused on bioclimatic envelopes, so looking at climatic variables associated with the locations, latitude, longitude, elevation, where species currently are found and are not found. And we have a very strong data set to do this because there are so many plots in the forest inventory and analysis data set, especially for such a wide-ranging species as ponderosa pine or Douglas fir. So we can compare, we can make a model associating the occurrence of the species with climate, then have climate shift under different sorts of climate models developed by climate scientists, and then see where new suitable conditions will occur. That gives us the prediction that Colorado would increase and Arizona and New Mexico would decrease, for instance. The advantages of this kind of work, very large data sets, very good fitting models. The disadvantage is, I think, kind of jumps out at you. Just because a model says, or just because it happens to be the case that, let's say, large parts of western Colorado become suitable for ponderosa pine where it doesn't grow right now, that doesn't mean the ponderosa pine has a way of getting there or of competing with other species, either those that are sort of, so to speak, left over from the old climate or other species that are invading and taking advantage of death of the previous community. So having a suitable climate is kind of a necessary condition, but it may not be a sufficient condition. Other factors are probably going to be pretty important. So this is you should view bioclimatic envelopes as a minimum kind of need. So what Crookston, Rehfeldt, and their collaborators did in developing Climate-FVS was to make use of these estimates of suitability in order to create what they called species viability scores. And there's a little graphic of it shown here, as well as the citation for the Crookston et al. 2010 paper, which is the description of Climate-FVS. And so they're essentially looking at the suitability of the site for each species under future climate, and then using those scores, which you can read off on the y-axis here of the graphic on this diagram, as indicators of how to adjust the existing FVS models of growth and mortality. So essentially, if we have ponderosa pine growing in a place where it's really happy now, like right by Flagstaff, Arizona at 7,000 feet of elevation in whatever our latitude is, about 33, it may currently have a viability score of 1, and it may have a very high likelihood of survival. Its growth would be exactly what the models that were measured and developed in that area would have predicted that it would have grown over the next 10, 20, 30, 40 years. But if that 7,000-foot elevation in the climate in the year 2060 starts to deteriorate relative to what we know about the climatic needs of ponderosa pine, then the species viability score can start to move downwards. and then the existing models of growth and mortality are adjusted. There's one more feature of Climate-FVS that's very interesting, this idea of adding in new species that may not be presently found on the site, but whose viability may be predicted to increase in the future. And we didn't use that in this particular study because we used the field regeneration data to look at how regeneration would occur rather than the auto-establishment. But it's a feature that is really useful, and we're using it in other studies. So where do we get the climate scenarios from? Well, we get them from the Get Climate-FVS Ready Data website, which was put together by the Climate-FVS group. It's a long address, so rather than put it on the screen here, if you just Google the underlined words there or just put Climate-FVS Ready, you will immediately find it. We had one scenario with no climate change that matches the previous work with FVS, and then we used the recommended combination of general circulation models, that is to say climate models, and socioeconomic scenarios that Crookston et al. Have put together in their basic package. They actually give you the power to look at whatever combination of models and scenarios you want. The models are what are predicting climate. The scenarios are the future idea of what society will do. Are we going to continue to pump out large amounts of greenhouse gases? Are we going to find alternative sources of energy? Are we going to come to international agreements to limit carbon dioxide outputs? That's what those scenarios show. We also developed scenarios of management based on manager interviews and based on our knowledge and participation of ongoing restoration efforts like the Forest Restoration Initiative, et cetera, to look at a set of realistic treatments that might actually be incorporated in management. And the treatments that we looked at a no treatment, no intervention approach. We looked at tree thinning from below, so coming back into stands, even though they had been treated perhaps at the beginning of the event, coming back in and thinning, and then looking at prescribed fire at different intervals, 5, 10, and 20 years. So right after the Rodeo-Chediski fire, these are the diameter distributions for the stands that Barb Strom measured in her work. In the left-hand panel, you see untreated stands. Now it shows living and dead trees, the white and black bars. Before the fire, they were all living. So when you look at that reverse J-shaped diameter curve on the untreated side, and notice there's a cutoff or a split axis here on the y-axis, that was those stands in the aggregate were very dense and very dominated by the smallest size class of trees below 4 inches. When you look at the treated stands, again, the white parts, the currently dead trees were alive before the fire. They didn't have giant trees, but they were at least a little more biased towards having some larger trees and to having thinned out many hundreds of trees per hectare in the smallest size classes. So we're starting with areas untreated before the fire. They burned severely, and most of those trees died, leaving a very open forest. And treated areas where the majority of trees survived and left behind a forest that could perpetuate itself. This is a field picture. This is from a untreated site, so there was nearly complete mortality in the foreground. We have alligator juniper at this site, so as a sprouting juniper, that's been a tree species that's been quick to take over. But as you see in the lower right, there is also substantial regeneration of ponderosa pine in this region of the Mogollon Rim. So this graphic now shows species performance predicted under the Climate-FVS model with these different scenarios. And so if you look at the top panel first, it has ponderosa pine, and it shows basal area. These are in metric units. If you multiply by a little bit less than 5, then you'll be in the ballpark for English units. So the starting point here might be somewhere around 55 or 60 square feet per acre. The black line is the line that shows how the ponderosa pine basal area is predicted to grow under no climate change. That's the same as the original Strom et al. Analysis. Then there's a series of lines with other dashed codes and whatnot. Those are 4 of the climate change scenarios, they come from different models, so they don't have the exact same, they don't fall in the exact same place, but they kind of fall into this moderate category. And the thing that they have in common is that they are not the scenario called A2. The scenario called A2 causes 3 different models to lead to a crash in ponderosa pine growth at the end of 100 years. So that's where the real distinction is between these climatic model and scenario combinations, between moderate and severe. And the severe ones are driven by the A2 scenario. If we look down at Gamble Oak on the bottom, the black line again is with no climate change. In the case of Gamble Oak, there are some climate change scenarios that lead to improved performance by Gamble Oak after 100 years, as opposed to the ponderosa pine, which was always reduced in growth by climate. So what we see is an individualistic response by different species, and this played out for the other species involved here as well, which were the alligator juniper and New Mexican locust, which implies that forest communities are not going to change as a unit, not as, say, pine-oak forest changing altogether, but rather the pines will be doing one thing, the oaks will be doing another thing. And of course, as one overlays disturbance on this, you could have insects that attack one species or the other, or you could have fires with differential effects. So we're likely to see a lot of reshuffling. And in our box over here in the lower right, we see the final point that under severe climate change, even for the oak, we see complete loss of these 2 dominant species. So now we take that kind of modeling framework and overlay our management treatments. And we get this big matrix that's in the lower left of this graphic. This is only a subsample of all the different combinations. So modeling projects lead you to these exponential multipliers of every combination of the model and the treatments and all this stuff. But this gives an overview of no treatment, severe change, and moderate change examples. So here we've pulled out an example with no climate change and no treatment. So you have on this upper panel here, the leftmost of the 2 that are next to each other, the top header here is T for treated. So these are treated sites. They're starting off at a relatively high basal area. In the absence of any treatment and in the absence of climate change, they end up back at being a pretty dense forest after 100 years. Conversely, the untreated areas start off at a much lower point. They also end up being a really dense forest, but if you notice, it's ponderosa pine that is the light-colored lowest fill on this graph. And so there's a lot less ponderosa pine dominance in these untreated sites than there was in the treated sites. This example right here replicates what Barb Strom found because her analysis used FVS with no climate change effect. And what she showed was these treatments made a big difference over 100 years. You still ended up with a dense forest, but one was a pine-dominated forest and the other was really a minority pine forest. So the formerly dominant species after that severe fire, and even after 100 years of recovery, no longer regained dominance. The sprouters in particular, all the other species, did much better. But as we were saying, our goal here was to incorporate climate. This was without climate change. Excuse me, got to do this one more before we jump to the climate change. This is what happens in that same setting if you add in a 5-year fire return interval. It maintains a forest that's very similar to the starting condition, dominated by pines, low basal area, open pine forest savanna. So that kind of an outcome is really underlying a lot of the forest restoration activities right now, just like forfry. The concept that by carrying out forest restoration activities that reproduce those processes that regulated the forest historically and over evolutionary time, that we'll get the same kind of outcome in the future. When we now add in moderate climate change, now we're looking at those scenarios that led to that in-between growth of the ponderosa pine and the Gamble oak. What we see here is a change. We see that if we were to use fire at a high frequency, the same as the historical frequency, 5 years is in the ballpark for the historical frequency, right in here where this black arrow is showing, we get some declines in forest over the time. But if we go to a somewhat longer fire interval, like 10 or 20 years, then we get what seems to be a more sustainable level of basal area, again dominated by pine trees because they're the most fire-resistant species over time. So this first conclusion in moderate climate suggests that we may be able to conserve these forests under an adjusted management regime. It doesn't fully replicate the historic management regime. When we turn to the severe climate change scenarios, then we have all scenarios leading to elimination of the pine component of the forest, and in many different combinations, including the prescribed fire treatments, complete loss of all 4 of the species that we started out with. We can do some non-burning treatments. Those are shown with the green arrows, and those leave oaks and junipers behind. So we end up with oak-juniper savanna, but those species are quite vulnerable to fire, at least in the FVS FFE modeling environment. So they are predicted to disappear unless we don't use fire. And in this case, our current fuel treatments do not have a persistent effect. We end up with a different ecosystem and need to be looking at a different management regime. In terms of carbon stocks, as this global conversation about forests and climate change goes on, one of the important issues is the role of forests in sequestering carbon from the atmosphere and holding carbon in stocks of large amounts of biomass. So when we look at this graphic here at the carbon stocks under the no climate change alternative, we see some difference between treated and untreated sites, the 2 colored bars, but we still have pretty high carbon stocks. In moderate climate change, we see about a 20% or so decline in carbon stock, but the real threshold comes between the moderate and the severe climate change, where we end up with a 94% decline in carbon stocks and really no difference, no legacy left behind from the treatments that were done at the beginning. So what we have replacing the forest is alternative vegetation, mostly grasses and shrubby species such as other oak species like Quercus turbinella. And Kristen Shive, one of the scientists contributing to this report, has done a separate Climate-FVS analysis using that auto-establishment feature that allows new species to come into the mix, and has shown that it's precisely those new species, which tend to be shrubby sprouting species, that are most likely to take over in these kinds of severe climate change situations. So in summary, we have uncertainty, obviously, about modeling climate. I mean, the world as a whole is working on trying to get a handle on how best to model climate and what kinds of socioeconomic scenarios are appropriate for the future. But we also have a lot of uncertainties about how we model forests and their responses to climate. But the potential magnitude of change is extremely high. So just within the range of alternatives that we've looked at in this study, or say that Rayfelt looked at in the analysis over the western U.S., there are large changes in the potential habitat of species that are currently dominant. Another conclusion is that species respond individually, so forest composition is likely to change on an individualistic basis rather than a wholesale movement of communities. Even under moderate climate change, it would be helpful to rethink our management approaches. The big problem with very frequent fires under the moderate climate change scenario was that every time you burn, there's some level of increased mortality. And coupled with the extra little bit of increased mortality associated with the moderate scenarios, that was enough to push the forest on a downward trajectory. When we get to severe changes, we have complete alteration. So the fuel treatments that we do now tend to have either positive effects or, in those severe situations, neutral effects. They're not making any difference, depending on those climate outcomes. One point that I neglected to make earlier was that even though those severe outcomes turn out really different, you can't tell that for a long time. We were looking at a 100-year graph of the ponderosa pine growth, and you have to go out about 40, 50 years before those treatments start to look different on the ground, which means that we're going to have to make some decisions now without being able to know what the answer is. And our last conclusions that we draw from this is that in our current policy, under NEPA, the way that we look at environmental assessments, we have to think about future scenarios and the consequences and cumulative impacts of management treatments. But for the most part, agencies are not mandated to consider climate change effects, and they often don't. We suggest that policymakers and managers should incorporate climate change when analyzing environmental effects of alternative actions. And the tool, Climate-FVS, is well suited to the kind of data that we have in western forests, the kind of training that we have to be able to use FVS. So our argument is that we should use it. And that brings us to the end, and we'll stop and see if there's any questions that I can answer.
Well, Pete, thanks so much for that presentation. A little depressing, but always good to get the truth out. So I'll start off with a quick question, and then I'll open the phone lines, and other people can add questions. Or if you have a question right now, you can go ahead and type it in the chat window. I've been trying to put in some of the URLs for some of the papers that Pete mentioned. So forgive me if I missed this in the presentation, Pete, but it seems like a lot of the modeling is just based on, let's see, drought stress and drought-driven mortality, but doesn't seem to include the increased risk of fire mortality, right?
That is entirely correct, yes. So this is how the stand will grow, and the only other things that happen to it other than its own internal dynamics, the way the trees compete with each other, comes from you putting it in. So you can put in that I want to see what happens with a severe fire in year 80 or year 100, but it's not independently giving a probability for that to happen every so often. Does that make sense?
Yeah, and would it be fair to say that the benefits of the treatments we're seeing here are in the tree competition and moisture stress, but as you sort of alluded to early on in the presentation, there are obviously fire behavior changing benefits of these sorts of treatments as well, and so those obviously could be incorporated.
Yeah, there are. And so if you do what I just said and simulate a severe fire, so we were simulating prescribed fire being used, the surface fire, every so often. But if you were to simulate a severe fire, then you would see the difference in the fuel structures. So as, for instance, all those sprouting junipers start to fill in the stand, your canopy bulk density starts to get really high.
Yeah. Okay, let me go ahead and unmute the phone line here. And so anybody else with questions, please go ahead.
Pete, this is Peter Brown.
Pete, are you still with us?
Yeah, go ahead.
Can you hear me?
I can hear you. Can you not hear me?
Yeah, I can hear you. Just a quick question on all of the modeling that you've done so far is based upon the range of ponderosa right now, right? So that doesn't include any type of ability for migration or anything like that.
Yeah. When you say the modeling that we've done, we're using the Climate-FVS model. We didn't, in any sense, create it. So it's really Rayfeld's work and Crookston's work that created this capability for FVS. And what that's based on is the presence and absence of these species, including gamble oak, for instance, and alligator juniper in the case of our forest, the presence and absence of these species on FIA plots across the West, compared with the climate at all plots. I don't know if that's quite answering your question.
No, that did. Thank you.
Okay. Anyone else? Xander, do we have all the folks whose names are listed on the Mittel thing on the line here?
They should be. They should be, because that's the only way to hear.
Okay.
You can call people out. You see names that are familiar. Go ahead.
Well, Barb Strom is is on the list, and she's one of the people who founded the original work here and did the first set of modeling. So I don't know if she had any comments to add, if she's actually on the line.
Hey, Pete. This is Barbara. Didn't really have any comments. I just wanted to clarify for anybody who was wondering why we didn't use a climate model in the first place. We did give it a try. Climate-FVS wasn't around at that point. We tried using the FVS BGC, but to my recollection, there wasn't a variant that worked very well with southwestern ponderosa pine. So we checked it out, but that's why we ended up not incorporating climate change into the initial study.
Yeah, that's an excellent clarification. And I remember very well that was quite a frustrating experience trying to work with that model.
It was, but I'm glad that Climate-FVS is around now.
Yeah.
Yeah, it seems very useful.
Question. Oh. Hi, this is Sharon Massa-Lopez at NAU. And I had a question regarding water balance. With forest restoration treatments, we're expecting a change in the water balance and perhaps more soil water storage. How could that change affect these models? You know, could it change the trajectory of the models if there's more soil water storage and more resilience in the forest to climate change?
You're saying with restoration treatments?
Right.
Because trees are being thinned out, and so there's less
competition for water, less use of water, more soil water storage, so that it could carry over from one year to the next to kind of even out the highs and the lows, and, you know, maybe make the trees more able to survive. So my understanding of where that would fall out relative to FVS as a model as a whole is that what we're doing with FVS is simply modeling the statistical relationship between how trees grow, how they're measured to have grown on permanent plots, versus their competitive environment, like the basal area and density of trees around them. The reasons why they grow differently, which is kind of what your question is getting at, you know, the way that a tree could use water because it's available, that doesn't show up, because what we're doing is taking a variable like basal area and showing with decades of data that trees that are growing in an environment with lower basal area around them grow faster. And one of the reasons for that is doubtless because they get more water. And another reason is they probably get more nutrients and more light, et cetera. But in this statistical modeling approach, which is the basis for models like FVS, all those things don't show up as separate variables. It's when people go to modeling ecological processes, in, for instance, the model that Barbara mentioned, the BGC, biogeochemical cycling model, that people try to simulate the reasons behind all these different processes. And those models are superior because you can try to understand all those reasons and you can directly respond to climate. Like if the climate gets drier, you can take water out of the soil and therefore show that the trees grow less. But they have a problem in that it's very hard to get precise answers to those kinds of models. And homogenize forest stands and treat them as if they were one big leaf. And they might be able to tell you a lot about the one big leaf, but they are often less useful to people who want to be able to compare different kinds of, you know, tree by tree, stand by stand management activities. So there's really two families of models there, and we're in the statistical side right now. Thank you.
Yeah, I hope that made sense.
Yeah.
We're just about at an hour, so if you need to drop off the call, we certainly understand. We thank you for your participation. there should be a survey that pops up when we end the webinar or when you drop off. And please do take a minute to fill out that survey. It really helps us understand what worked well and where we can improve. For those of you who can stay on another minute or two, I think Pete might be willing to answer another question or two if you want to just speak out.
Yeah, and I just want to say thanks to all of you for attending and participating in this. And I'm really happy that it worked out and it didn't drop the call. And they told me at the end of the day today that this building closes about now and that this room has a motion-sensitive alarm in it. So I'm really glad that didn't so fun.
Well, so if you need to leave, Pete, we understand. But thanks for a great presentation.
You'll hear when the cops pull me out.
Good chance to practice your French.
Yeah.
Other questions?
No, I'd just like to say thanks too, Pete. That was great. And the model, so something definitely to use, it sounds like. So looking forward to trying it out someday. Yeah,
I mean, it's Crookston and Rayfeld, they've done a lot of good work with this. It's, you know, the problem with climate change issues and with climate change modeling is there is a lot of uncertainty and we don't know which of these scenarios is going to work out and all that. So we're not saying that you need to pick one and, you know, but just to have that perspective start to be built into future planning, I think is really important.
Well, as you said in the last comment, I think in terms of management, you know, understanding of something like this, it does sound like it's going to be something that would be approachable for most everybody.
It is, yeah.
Is there good training available for the climate model? I mean, do you feel like, I wonder if that's something that consortium maybe we should have a webinar or a training session on that, or is it relatively self-explanatory if you can use FVS?
That's an interesting question. So we did not go to any formal training, but we did get a lot of help from the help desk and also from Nick Crookston with specific questions. And then having Andrew Sanchez-Metter involved too was extremely helpful because he knows a lot about Climate-FVS, but he also knows all the right people to ask within the Forest Service. But I think if there are people interested in trying to make something of an effort or put together a workshop, I think Nick Crookston would be interested in helping. You know, they created this for it to be used, not to sit on the shelf.
Yeah, well, maybe that's something we should look at and talk to them a little bit about whether the right approach is an add-on to, say, the resiliency workshop or a webinar format or what would be most helpful. Because for me, I know that's something I'd be interested in dipping a toe into some of that work, but the struggle of FVS is not the easiest program to use, and adding another element of complexity is a little daunting.
Well, I agree with that, but 90% of what you're doing with Climate-FVS is FVS. So for the people who are already there, the people doing silvicultural analyses and EAs and so on, you know, they're most of the way there.
Great. Any other questions? Okay. Well, let's maybe we'll go ahead and end it here. Thanks again, Pete. I'll go ahead and shut down the webinar, and maybe you can get out before the alarm goes off.
Thanks very much, Sander. Thanks to all of you.
Thank you, Pete. Thanks, Sander. Bye.
Thanks.
Well, thanks.